You have this incoming URL and it's going to get classified into one of the K front queues. It'll pass through that front queue. By the way, each of these queues is literally a queue. Each front queue is literally a queue and each back queue is literally a queue. So it's just a simple first in, first out data structure. The URL will enter at the back of whatever queue it's sent to, and then as the URLs in front of it get popped out, and when its term comes, this particular URL will also be popped out, and then it will be sent to one of the B back queues, and then at some stage it will be pulled out of the back queue and then sent to the crawl thread, which is requesting for the next URL. Okay, so this was the URL that will be handed over to the crawl thread, which will then go and fetch the document at that URL. Now, what are these front queues and what are these back queues? Well, I just showed you that the URLs flow in from the top into the frontier. By the way, this particular architecture is called the Mercator architecture because Mercator is the name of one of the early crawlers that was built for the web. So this is the architecture for the Mercator crawler. Now the front queues are the ones that are going to manage prioritization. That means these are the queues that are going to decide so these are the queues that are going to influence the rate at which you ping the same web server again and again. Okay, so they're going to prioritize that this particular web server needs to be sent a fetch request again and again and again because it happens to be a news web server. So this particular URL, this particular web server needs to be crawled at a faster rate. Whereas that particular server should not be crawled at a very fast rate, either because it's not being refreshed very often. Okay, so if a particular web server is refreshing its pages very often, you may want to crawl it at a higher rate. On the other hand, if a particular web server has very authoritative pages, that's the other that's the other factor that can influence that that you want to crawl it again and again. If it's a very, very authoritative page, then you want to be sure that you have the latest copy of it. And if it's not just authoritative and it's also changing very frequently, the web pages are changing very frequently, then you'll crawl that website very often. So the front queues are going to manage the prioritization. And actually, before explaining, let me just directly jump to what this figure is showing. So this is just the top part of the figure that I showed you earlier. This is the top half of the figure. What's happening here? There is this incoming URL, and this URL will be assigned a priority between 1 and k. So there are k front queues over here, and this incoming URL will be assigned an integer or a priority, and based on what priority it's assigned, it's going to enter that particular queue. Now a priority 1 queue is priority 1 queue contains URLs for web servers that need to be crawled very, very frequently. Okay, so think of this priority 1 queue, for example, as URLs corresponding to news web servers or news websites. Okay, they need to be crawled very frequently, whereas priority k the priority k queue contains URLs for web servers that need to be crawled very, very infrequently. So how do you assign such a priority? Basically, you keep track of how frequently the web pages are changing on a particular web server. And if you notice that the refresh rate is pretty high for any particular web server, and if the pages happen to be important enough, then you're going to crawl those web servers more often. So what you're going to say is, anytime a URL comes in that corresponds to a page on that particular web server, I'm going to give it a priority of 1. Okay, so all URLs on, say, news.cnn.com would be assigned a priority of 1 because cnn.com has a high priority. It's a news website. Okay, so cnn.com/something comes in, it's going to be assigned a priority of 1 and it's going to enter this particular queue. Is that clear? Now, so basically we have these k priority queues over here. Now how do items get pulled out of this of these front queues? One strategy could be to say I'm going to pick out the item from here first, then the next time I'm going to pull it out from queue number 2, then from queue number 3, then from queue number 4, and so on. Now clearly that's not what we're going to do, because the very fact that this queue has a higher priority means that URLs that are in this particular queue have a higher priority than URLs in other queues. So I need to be pulling out URLs from queue number 1 at a higher rate than URLs in other queues. So when a URL is requested from the front queue, the number or the ID of the queue is decided based on techniques which give the queues with a lower number a higher priority. Okay. So here are two ways in which you could do this. This is one policy you could follow. I'm going to pull out an item from queue number 1, then I'm going to pull out an item from queue number 1 and then from 2, then from 1, 2 and 3, then from 1, 2, 3 and 4, then from 1, 2, 3, 4 and 5, and so on. So notice that this is the sequence I'm following: 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, and so on. So I'm pulling out items from queue number 1 most frequently. Then I'm pulling out items from queue number 2 slightly less frequently. And then the rate at which I'm pulling out items from 3, 4, and 5, and so on goes on decreasing for queues with the lower and lower priority. Okay, so that's kind of round robin strategy. Another strategy could be that I assign these queues different probabilities. Okay, so I'll assign this particular queue the highest probability. That means I'll flip a coin and I'll say that if my coin falls into the range 0 to 0.5, well, forget about a coin. Let's think of a random number generator. So I'm going to generate a random real number between 0 and 1. If my random number happens to fall in the range 0 to 0.5, I'm going to pull out the next URL from queue number 1. If my random number falls into the range 0.5 to 0.75, then I'm going to pull the URL from queue number 2. If my random number happens to fall into the range 0.75 to 0.85, then from queue number 3. So you can see that queue number 1 has half the range. Okay, so this is the range for queue number 1. If my random number falls into this range, I'm going to pull out the next URL from queue number 1. Queue number 2 has a smaller range, so it's less likely that my random number will fall into this region than compared to this region. Queue number 3 will have an even smaller range. Queue number 4 will have an even smaller range. 5 will have an even smaller range, and so on. Right? So you can assign different probabilities to pulling out items from different queues. Larger probabilities for queue number 1 than to queue number 2, and a larger probability to queue number 2 than to queue number 3, and so on. So this is a this is a randomized way in which you can pull out items from queues, but clearly it's biased towards higher priority queues. Okay, so look back at this diagram. Again, remember what's happening. Based on what web server the URL corresponds to, it's going to be assigned a particular priority. That this priority will be determined by how authoritative the pages on that web server are and how frequently they are changing. So based on that, these priorities are decided, and the URL will be assigned one of the queues. And then the way in which the items will be pulled out of these queues is based on either a randomized process or a round robin process, that no matter which of these two you choose, it's going to be biased in towards queues with higher priority. So these will be the queues from which the URLs will be pulled out most frequently. Any questions about what we have discussed so far? And this is the top half of this particular picture. So what's happening here is you are giving, so note these two requirements. Okay, freshness is what we are trying to achieve via the front queues, because the front queues are ensuring that some servers are crawled more often than others. Even though the URLs may be going into the front queues in any order, but the way in which they are coming out of the front queue is in a biased order. Okay, so the order is biased towards pages that are residing on web servers that change very often. The other thing that we want to achieve is politeness. We don't want to hit the same server too frequently. And that is something for which the back queues will come into play. Okay, so now let's look at the back queue. This is slightly more complicated than the front queue. So you have a bunch of B back queues, and again, when a URL is pulled out of the front queue in that biased order, it's going to enter one or more of these back queues. Now, notice that these front queues could have contained URLs belonging to different servers, right? As long as all the servers have the same priority, all the URLs for pages on those servers will also have the same priority, and so they will enter the same queue. So it's possible for a single queue over here to contain URLs from different servers, just because the different servers were assigned the same priority. Okay, so that's just an observation about the front queue, because that's not going to be true for the back queue, as you'll just see. So what do we want to achieve via these back queues? We want to ensure that once we ping or once we send a crawl request to a particular web server, we are going to give that server a time gap before which we don't send another URL to the same server. Okay, so here's what the back queues are. So each back queue corresponds to one particular server. Okay, so this could be the server www.cisco.com. Okay, this is back queue number 1. Back queue number 2 could be the server www.stanford.edu, and so on. This particular back queue could be the server www.cnn.com. Okay, so all the URLs on which are of the form www.cisco.com/something something, they are going, when they emerge from the front queue, they are going to enter this particular back queue. All the URLs on Stanford's website are going to enter this particular back queue, and so on. Now we are going to maintain, notice there's something called a heap here. Okay, so this is actually a data structure, the heap data structure, which we have encountered before in the course. And this is actually a min heap. So what is a min heap? If you recall, a min heap is a data structure in which your keys are such that the key that is the key of a node is less than the key of both its children. Okay, so the smallest item in the heap is at the root of the heap. Now what are the keys going to be here? So firstly, what will the heap contain? So this heap will be of size B. Okay. This heap is going to be of size B. That means it will have B vertices in it. Each vertex corresponding to one of these back queues. Or in other words, each vertex corresponding to one of these servers. And the value of the key is going to be the timestamp, the threshold. I mean, let me just call it the threshold timestamp. So this is the value of time before which I'm not allowed to hit that server. Okay, so for example, an example of a timestamp could be 10:15 p.m. for www.cisco.com. Okay, that means I'm not going. So this particular vertex with a value of 10:15 p.m. okay, corresponding to the server www.cisco.com is indicating that I'm not allowed to send a query to www.cisco.com before 10:15 p.m. Obviously, this is just a crude example. The actual timestamp could be in seconds or milliseconds also. So what does it mean for, so clearly the very fact that this is a min heap means that this particular root is the server which has the least value of the timestamp. So this is the server that I'm allowed to query next. Okay, before I query any of these other servers, I have to send a fetch request to this server because this is the server for which the timestamp value is the least. And as I mentioned before, we want to make sure that we are not sitting idle. So the moment we are allowed to query a particular server, we are going to go ahead and query that server for the next URL, assuming that there is a a URL in the queue for that server. Okay. So we will extract the minimum element from this heap, and that's going to tell us which is the next server that we are allowed to query. Then we will go to the queue of that server and pull out the URL at the head of the queue. So if the next server is www.cisco.com, I'm going to go to the queue for www.cisco.com and pull out the first URL in the queue. And this is the URL that I'm going to send out to the fetcher. So the fetcher will take this URL and then fetch the document for that URL. So a few details. There's going to be one queue, sorry, in the heap that I just showed you. This is just a slide corresponding to what I told you. There's going to be one node or one entry for each server or for each back queue. And the key value, the key of the entry is going to be the timestamp, the earliest time at which the host can be hit again. Now, how will this time be determined? Obviously, it has to be determined before I insert that new node into the heap. So this time is going to be determined based on when was the last time I hit that server, plus the time gap that we decide to give to that server. Right? Recall that we talked about this common heuristic that we want to give a time gap between successive requests that is proportional to maybe 10 times more than the latency of the last request from that server. So if I know when I queried the last server and I know what the latency was for that request, I can take that time, add 10 times the latency to that time, and I'll get the next time that I can query the server. Okay. So how is an item going to be pulled out of the back queue? Well, suppose a crawler thread wants the URL frontier to give it a URL, the next URL that it wants to fetch. Well, we will extract the root of the heap. That's going to give us which server we can hit next. We will fetch the URL at the head of that particular server. Okay. Now here's the point. Suppose I pull out that URL. Okay, suppose it's www.cisco.com and I pull out the URL, and now this queue becomes empty. What will I do? I will then go to the front queue and say, give me the next URL from the, I'll ask the front queue to give me the next URL so that I can put it here. Now, suppose the next URL happens to be of some other website. Let's say it's www.stanford.edu's URL, right? Because it's not guaranteed that the next URL that I'm going to get from above, from the front queue, is going to be a URL for cisco.com. So if it's for some other server, I'm going to insert that URL into the queue for the other server. And then I'm going to go back to the front queue and say, give me another URL. Until I fill up, until I get an element that I can insert into this queue, because this queue is empty. Right? So I want to ensure that all of these queues are non-empty. So the moment any queue becomes empty, I'm going to ask the front queue to keep giving me URLs until I can find one that can be stuffed into this queue. Now, it's not necessary that the URL that I will put into this queue is cisco.com because imagine how many queues you need, how many back queues do you need? Okay, if you had a separate back queue for every web server on the web, you will probably have, you'll probably require millions of back queues. But what we're going to do is we're going to have only a small number of back queues, a relatively small number of back queues. And if Cisco's back queue becomes empty and I get a URL corresponding to a server which does not correspond to any of these other b-1 back queues, then I'm going to relabel this server and I'm going to say, well, now it's not a Cisco server, a Cisco's queue anymore. Now it's going to be, say Juniper Networks' queue or some other company's queue, some other web server's queue. Okay, is that clear? So we are going to check. So when we fetch a URL from the head of the queue that we just pulled out from the heap, we will check if the queue is now empty, and if it is empty, then we want to ensure that it does not remain empty. So we are going to pull a URL from the front queue, and let's say that URL happens to be a URL for some other server. Then I'm going to insert that URL into the queue for that other server. And I'm going to go back to the front queue and ask it to give me another URL. And if this URL happens to be a URL for cisco.com, good enough. I'm just going to add it to my Cisco queue. But if it happens to be for some other website which is not represented by any of these b-1 servers, then it's as if this Cisco queue is no longer a Cisco queue. Now it's become a queue for the other website, for the other web server. And when I create this queue for a new server, okay, in this particular way, instead of Cisco, let's say it becomes a queue for Juniper's website, I will have to add an entry to the heap and say that, well, this entry corresponds to queue number 1, but queue number 1 is now denoting Juniper. So the timestamp on the node that I will insert into the heap will be the timestamp that will be calculated based on when I hit Juniper server last, plus the latency that I want to give that server, before which I can hit it again. And then I'll insert that particular node into the heap, and it will descend to the appropriate level to maintain the heap property. And obviously when I pull out a URL from the server, even if that node exists in the heap, obviously I'm going to pull out a URL from the back queue only when I extract the minimum element from the heap and I find that it corresponds to that particular back queue. Then I'm going to send out that URL and I'll obviously update the timestamp, right? So if this back queue is no longer, so let's say I pull out a URL from cisco.com over here and this queue is not empty. There are still more URLs to come in this queue. Then I will update the timestamp for Cisco and then reinsert that node back into the heap. So obviously now it may not remain at the top. Now it could be somewhere near the bottom. Some other node may come at the top because its timestamp may be earlier. Okay, so obviously when we'll need to maintain this table because when we extract an item from the heap, we have to know which queue to go to. Okay, so if the item says so let's say I extract the minimum element and that's the timestamp. I'm going to get the timestamp value, whatever it is, and I'll also get to know which is the name of the server it corresponds to. And then I'll have a table which will tell me for cisco.com, the name of the queue is, the number of the queue, back queue is 3. So I'll go to queue number 3 and get the next URL from there. Okay, so this is the last slide. We want to keep all the crawler threads busy while respecting politeness. So note that we are enforcing politeness in this particular way. Okay, by maintaining this heap, by having these timestamps. And you can see from here that it's not necessary that we will query the same server very frequently, right? I could, if I'm getting cisco.com's URL, then the next time I fetch a URL from the back queue and send it out to the crawler thread, it will be probably be from some other server because now the timestamp that will be smallest will be for some other server. So we want to keep all threads busy while respecting politeness. And this is the way we can do that. We can enforce this timestamp and we will give the thread asking for a new URL, a URL from some other server. Instead of cisco.com, we'll give it, the next time it asks, it'll get a URL from some other server. And the recommendation of the Mercator crawler is that the number of back queues that you maintain should be 3 times approximately as many as the crawler threads you have, the number of crawler threads you have. Okay, so if there are 300 back queue, if there are 100 crawler threads, you can have 300 back queues, and this empirically works well. That way all the 100 crawler threads can be kept busy, and at the same time you can enforce politeness, right? So remember that the back queues are enforcing politeness and the front queues are enforcing prioritization or freshness, right? Prioritization or freshness. How frequently you want a particular set of servers to be, crawled again and again, and at the same time giving each server its due latency. Okay, so a combination of these front queues and back queues, as you can see from this figure, is what's going to have the crawler satisfy both of those.
Excuse me, sir.
Yeah.
Sir, could you kindly stop now?
Okay, I'm actually done. So if you have any doubts, you can watch this video again. I think we are basically done with crawling. So
yes, sir.
We are going to have another class tomorrow, so you can ask any doubts you had.
Yes, sir. Thank you.